Welcome back, everybody. This is going to be part 2 of the periodic table. In this video, we're going to be talking about the different groups and the properties that each group has, such as the alkali metals or the representative elements. And we're also going to be discussing the electron configurations and how we can use the periodic table to help us identify these electronic configurations a little easier. So you're going to see a little review of electron configs here. Before we get started, let's go ahead and look at the objectives for this lesson. So we want to go ahead and describe what information is provided from the periodic table. We want to classify elements based on their electron configuration into those groups. And then we're going to distinguish representative elements and transition elements. So I want you to be able to identify where we find those on the periodic table. Now, the first thing that we notice when we look at the periodic table is we see these little boxes. And each periodic table is a little different in the way that this information is structured, and some periodic tables don't even have some of this information. But by now you should be familiar that usually the darkened number is the atomic number. Sometimes on some periodic tables you'll see these electrons in each energy level. So remember, the first energy level only holds 2 electrons, the next one holds 8, and this one, the third one, we only have 1 electron in there. Now notice if we add these numbers up, we've got 2 plus 8 plus 1 is 11, and that means that the number of electrons is the same as the number of protons. Just a little review from our previous chapter. Then of course we have the element symbol, the element name, and the average atomic mass, which we sometimes see as also referred to as the average atomic weight. One thing that I want you to be aware of and to recognize is that electron configurations in groups, there's a trend to them. So elements can be sorted into 4 different groups based off of these electron configurations. We'll generally call them a noble gas, a representative element, a transition metal, or an inner transition metal based off of their electron configurations. Now, when we talk about representative elements, these could be elements that are in group 1A through 7A. And each group does display a wide range of properties. And so we would want to say that they're representative. So some are metals, some are nonmetals, some are metalloids, some are solids, others are gases or liquids. So they have a wide variety of properties. And what makes these things, why we call these representative elements, is that their outer S and P electron configurations are not full. So if your S or P is not full, that's a good clue that it's a representative element. So when we look at the periodic table, the first ones we're going to look at are these representative elements. So you can see the little yellow circles are showing you all of the families or groups that we would call representative elements. Again, this first one over here we call the alkali metals. These are the alkali earth metals. Over here, these were the halogens that we discussed. Then these, depending on their, now I've just drawn in the representative elements here. So here's boron, carbon, nitrogen, and oxygen. So I would call this group here the boron group. This would be the carbon group, the nitrogen group, and the oxygen group. And all the elements that are in the bottom of this column have similar characteristics to boron. All of these have similar characteristics to carbon. Now let's get more specifically talking about groups of elements, or sometimes they're referred to as their family names. The first one, you're going to see at the top of the column that there's this Roman numeral, and it says Roman numeral A, and this group is referred to as the alkali metals. These form a base or alkali when reacting with water, so they just don't dissolve, they have a reaction. Group 2A are considered the alkali earth metals. They also form bases with water, but they do not dissolve well, and they're called earth metals. Then the next group that I want you to be aware of is 7A, and this is the word halogens, and this means salt forming. So when we think of sodium chloride, that's salt, and chlorine is one of the elements that appears as a halogen. Now, the thing that I want to just mention really quickly, and we should have noticed from when we did our periodic table basics activity, is that the group 1 are the alkali metals, but notice that we don't include hydrogen in it again because hydrogen itself is a gas and it's not a metal. Then we see the group 2A are the alkali earth metals. So notice we're repeating these, so it's going to be important that you can just identify saying that the first column, alkali metals, second column, alkali earth metals. So one group we haven't talked about are the noble gases, and these are the ones that we find in group 8A. We call these also inert gases, and it's because they rarely take part in reactions. They're very stable, so they don't react. Remember, we also talked about that their electron orbitals are full, so they don't need to react with anything because these guys are already happy because their electron shells are full. Noble gases have an electron configuration that has the outer S and P sublevels that are completely full, again, meaning that they're happy. Again, we said the last column was called the noble gas configuration, or noble gas, and these were inert elements because they had full electron configurations. This light blue group here is called the halogens or salt formers. Now the next group that we're going to talk about are these transition metals, and we're going to notice that they have a B around them, and so they kind of appear in the middle of the periodic table, and we're going to point these out more specifically with a picture in a minute. But transition metals have electron configurations that have the outer S sublevel full, but now we're starting to fill the D sublevel. So there's a transition between the metal area and the non-metal area, and so some good examples of transition metals are gold, copper, and silver. But remember, the idea is if you're a transition metal, you're starting to fill these D sublevels. Then we have these ones that are called the inner transition metals. And so if you've ever noticed, like there's two rows that are like kind of removed from the periodic table and like shoved underneath, these are the ones that we would call the inner transition metals. And so these have an electron configuration that have an F sublevel are starting to be filled. So again, inner transition metals, F sublevel being full. And they're formally called the rare earth elements, but this is not true because some of them we now know are very abundant. So the first thing that I want you to notice is that this group of white elements here, these are called the transition elements. But then if we look at this bottom, these two rows, these are the ones I was mentioning earlier, these are the inner transition elements. And if you look at them, we would stick this row right here, it would fit like right in up here. And then this one would fit in right up here. So go ahead and just take a quick look at your periodic table, look at the atomic numbers for like this one, and then see how it would fit in up here. Look at this one, see how it would fit in up here. Now the thing that we want to do here on this slide is to look at the alkali metals, and we're including hydrogen now in this first group. And what I want you guys to do is to look at these electron configurations and notice what do they all have that are similar. And I'm hoping you're all saying, oh, look, the white. So we have S1, I'm sorry if you can't read that, S1, 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 and so on. So all of the electron configurations for these elements in the same group, they all end in S1, meaning that there's only one electron in their S suborbital. So let's talk a little bit more about this. So elements, we would consider them to be in the S block if they're alkali metals or the alkali earth metals, because all of their electron configurations are going to end in S1 or S2. We really should include helium in here, but it fits better in a different spot since helium has the properties of a noble gas. It has a full outer shell. So sometimes you'll see maybe representations when we talk about the S block of putting helium over here. So now we're going to watch a little bit of one of the Khan Academy videos. This one is called Orbitals, and it's going to go ahead and explain these S, D, P, F blocks and kind of how you can identify them.
Figuring out the configuration. So the question arises, what happens when we start going to the D and F subshells? So the general way to think about it is the energy shell you're in is equivalent to the period we are in the periodic table. So if we were to do, just so it all fits on one page, the periods were written out here to the left, but then I wouldn't be able to finish the whole table. So this is period 1. Let me write this in a darker color. So period 1, 2, 3, 4, 5, 6. I think I barely am fitting on the page, right? So each row is a period, and then for the purposes of figuring out electron configuration, we did this in the last video. We want to put helium. Let me just copy and paste exactly helium. We want to put helium in the S block, so we want to put helium right there. The reason why, just in case you're curious of why helium is put there in the periodic table is because it has very similar properties to the elements, to the other elements in this column or this group. Each column is called a group, and we'll talk about valence electrons and why that leads to different properties. But for electron configuration purposes, we can put it in the S block, and that's not too hard to remember because it's just one element, and it kind of makes sense, 1s1, 1s2, etc. And what you do is you draw blocks around them. So see, this is, I've said multiple times already that this right here is the S block. S block. This over here on the right is the P block. That's the P block. And then this in the middle right here is the D block. This is the D block. The D block. D block. And so if you want to figure out the electron configuration of any atom, you just have to, the way you think about it, they fill in this order, but when you say, let's say this, when you go from calcium would have filled out the 4s2, right? 4s1, 4s2. So if I just do its fourth energy shell, it looks like this. Calcium, it's 4s2, 4s2, and then you start filling the D block, right? Oh, what did I say? So that's calcium. So I wanted to figure out the electron configuration for iron, right, which is in the D block. So it turns out, and this is kind of an artifact, and I'll do a little bit more detailed video on this in the future, of that it actually goes and backfills the third energy shell because all of a sudden the d orbitals can kind of fit in the gaps of the third energy shell. So what you do is you go one energy shell above it. So whatever period you're in the d block, you go one minus that. You go that period minus one to figure out what energy shell the D block is filling. So iron has 1, 2, 3, 4, 5, 6 elements in the D block. So it's going to have D6, but it's not going to be 4D6. It's going to be 3D6. It's going to be 3D6. And I figured that out because it's in the fourth period, and I subtracted 1 from that. So this is the kind of the highest energy 8 electrons in iron, right? 4s2, 3d6. If I said what are the electrons that are in the outermost energy shell, I would say that there are 2 electrons in the outermost energy shell for iron. But if I were to say which energy cell has the highest energy electrons, it would be these. Let me actually do the whole electron configuration for, let me pick up another one just so it's let me take, I don't know, what is this? This is copper right here. Let me do copper right there. So the highest energy electrons it has are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, let me not do copper because copper does something very interesting in real life. So it's one of the few things that kind of is a special case. So let me do a different one. Let me do I don't know. Let me do the whole thing for iron. Sorry to be waffling around so much. So if you wanted to do the entire electron configuration for iron, it would be 1s2. That's the first energy shell. Now the second, let me do that in magenta right there. 1s2, and then in, let's say, in orange, then you have 2s2, and then you have 6 in the p section right there. So 2p6. Now we're in the third energy shell. The third energy shell, let me go switch to this bluish color. So then I fill up 3s2. Remember, this is the S block. Then I fill out 3p6. 3p6. Fill out those right there. Right? 1, 2, 3, 4, 5, 6. Now I'm going to add these electrons. Then I add, let me pick a nice green. So then I go to 4s2. So it's 4s2. And now this was the interesting thing, that this whole, the D block is interesting. Now I fill out another D block. It's my first D block, 1, 2, 3, 4, 5, 6. But it won't be in the fourth energy shell. It'll be in the fourth minus 1 energy shell. It'll be in the third energy cell. So this will go to 3d6, just like we did at the beginning of the video. And so it's in the third energy shell, so I would actually write it here. I could write it, if I wanted to write 3d6. So if I wanted to write things in order of which energy shell they are, I could have written it this way. If I wanted to write it in order of the highest energy electrons, remember the shells are kind of the best way to visualize it, how far away we are from the nucleus. So in this case, these higher energy electrons are going to be further in the nucleus, even though they take it's a higher energy state to be in. These higher energy electrons are going to be further in the nucleus, even though they take it's a higher energy state to be in. If I did it in terms of energy state, I could rearrange these two. But in most of chemistry, what matters is what's in the outer shell. So it's interesting that although we filled our 4s2 here, and then we kept adding more and more electrons, those electrons were just filling a lower energy shell. So if we, in this atom, in the case of iron, when we talk about the electrons in the outer energy shell, and those are called valence electrons, and these are the ones that react. So that these are called valence, let me do this in a better color, valence electrons. This iron has 2 valence electrons because the outer shell is 4s2. Even though it had these, even after filling 4s2, it had 6 more electrons, but those kind of backfilled the third energy shell. So that's one way. And then, so you might say, oh, well, what happens when we go to the F shell or the F block? So that's these down here. So a lot of periodic tables, you see these lanthanoids and actinoids down here, and they're supposed to fill in the gap right here. And that might be a little hard to visualize, and I'll show you why they do that. You could have just as easily made a periodic table that looks like this, where you insert them in, where you push everything to the right and you insert these in. But obviously this type of periodic table is a lot harder to fit in. You could have done the same thing with the D block, actually. So, you know, this one, this is the S block, this is the F block, and this is the D block, and then this is the P block right here. This is the P block. And when you're dealing with the F block, so let's say we wanted to figure out, I don't even know what element this is, the electron configuration for this, their atomic symbol La. So in the F, it's filling out this last incremental electron fills the F block. So it's F, it has 1 in the F, maybe I should do it in lowercase. So it has 1 in the F orbital, and this is the 6th period, but with the F block you subtract 2. So you subtract 2 from it, so it'll be 4F1, and then 6S2, right? The S block, you just look at the period, 6S2, and then if you were to keep going back, you would then go to 5P6, so then it would be 5P6, 5P6, and then it would fill out these 10 in the D block, right there, that are in the 5th period, but remember you subtract 1 from the D block, so it'd be 4D10, and then it's 5S2, 5S2, and you just keep going back that way. And it seems complicated at first, but just remember, when you're in the S or the P block, you just look at the period you're in, but then when you start filling the D block, it fills in this is the D block, it fills in a subshell that's 1 lower, and when you start filling the F block, which are these really large elements, you start filling a subshell that is 2 lower. And so maybe in the next video I'll do a couple of these electron configurations because I think I'm already out of time. And I'll actually show you another way to figure this out that's often covered in some chemistry classes. See you soon.